All right, so in an experiment, the goal of an experiment is for researchers to see a difference in the response so large that it's unlikely to happen just by chance alone. So we're going to talk about the term statistically significant. So what exactly does that mean? That means that we conduct an experiment that the treatment or the response did not happen by chance alone. There was actually a reason that people's pulses were higher or babies were born at a healthier weight. This is a little bit confusing because when we say just by chance alone, so when we do an experiment and we're giving people caffeine and not caffeine, there are some people's pulses who are naturally going to increase just by chance alone, not because of the caffeine. But the goal is it's statistically significant if everybody's or a majority of the people's pulses increased by the caffeine, and it wasn't just one or two people's pulse rates that increased. That would be just by happen if I had a whole bunch of people in a room, there's a chance that one or two of them, their pulses increase. So statistically significant, didn't happen by chance alone. There was a reason that the response variable acted the way they did. So statistically significant, we're going to be using this throughout pretty much the rest of the year, is an observed effect so large that it would rarely happen by chance alone. A statistically significant association in data from a well-designed experiment does imply causation. So if your experiment is well-designed, you've used the 4 principles of experimental design, we can now have a cause and effect, okay? We can say that caffeine actually increases their pulse rate. So just remember, if you have an observational study, it's not an experiment, therefore you can never have cause and effect from an observational study. All right, so let's just think back to the caffeine experiment. How will we know if it's statistically significant? We want to know, is there convincing evidence that caffeine actually increases the pulse rate? So in other words, is the difference in mean pulse rate statistically significant? So is the difference in pulse rates before the experiment and after this experiment statistically significant? Did the caffeine actually cause the pulse rates to increase? So how would we do this? How would we make sure that it is in fact statistically significant and isn't just by chance alone? I would repeat this experiment many times, and I could make a dot plot of the differences in mean pulse rates. So when I say repeat it many times, that means there's going to be a lot of experimental units or subjects within my groups. So if the pulse rate increased by 4, how often did you get this difference? If you didn't get it often, it's not statistically significant. So if one person's pulse rate increased by 4, that's basically like saying that maybe just happened just by chance alone. Just by chance, okay, somebody's pulse rate in the group increased, okay, but did it happen a lot or did it only happen once? If it only happened once, it's not statistically significant. He's just the oddball in the group. But if it did happen often, it is statistically significant. Now, the experiments that we talked about were the most simple statistical experimental designs. All right. However, just with sampling, there are times when the simplest method doesn't yield the most precise results. So think about some of those things we were talking about that are sort of lurking in the background. So for example, when we're talking about the pulse rates, maybe males and females actually respond differently to caffeine. Maybe people that are athletes versus not athletes respond differently to the caffeine. If we identify those as variables that could possibly affect the response, how do we account for that in our experiment? We do it by something called blocking. So what blocking is, it's a group of experimental units that are known before the experiment to be similar in some ways, some way that is expected to affect the response. So if we think that male versus female is going to affect how the caffeine affects you, we are going to separate the males versus the females before we randomly assign the treatment to the two groups. So in a randomized block design, the random assignment of the treatments, okay, is carried out separately within each block. So within the male block and within the female block, we would randomly assign caffeine cola versus non-caffeine cola. How do we choose what blocks to form by? Because there's so many variables that could potentially affect the response variable. We form blocks on the most important unavoidable sources of variability. So think about your lurking variables and what is going to affect the response the most. If you don't think male versus female is going to affect the response very much, don't use that as your blocks. However, if you think that potentially maybe athlete versus non-athlete is going to affect the response, then you would block it by athlete versus non-athlete. Now, what will this do? Randomization will then average out the effects of the remaining lurking variables. So let's say that we think athlete versus non-athlete is important, and we think maybe male versus female would be, that's potentially, but hopefully by randomizing them within the two groups, it's going to balance those effects out and allow for an unbiased comparison of the treatments. Okay, so how do we know how to block? When we're doing experiments, to do the best experiment we can, we want to control what we can. All right, so we're going to control maybe the environment, maybe everybody's sitting when we're doing the experiment, everybody's going to be sitting down, no one's going to be moving so that, maybe somebody's pulse rate isn't increasing because they're walking back and forth around the room. That's what I mean by control. We're going to block what we can't control. We can't control if they're athletes or non-athletes. And then we're going to randomize to create groups that are comparable, so they're a good representation of the population. All right, so how could we improve the caffeine by blocking? Now, we just talked about this. Men and women might have different resting pulse rates. So blocking by gender helps to eliminate gender as a confounding variable. So I'm going to block male versus female. Then males and females are each going to be randomly assigned to caffeine or no caffeine. When blocking, the block should be very different. You shouldn't have two blocks that are similar, and there's no point of blocking. At the end of the experiment, you compare the results of everybody. You don't just compare the blocks. Okay, so that's important. And we just talked about how do we know which variable to block by? We are going to block by the variable that we think has the strongest association with the response variable. So if we think gender is really going to affect our pulse rates, then we want to block by gender. When we create blocks, we're going to create them on the most important, unavoidable source of variation. We can't change if they're male versus female. However, we can control for sitting down versus standing up. We can say everybody has to sit down. Randomization will average out everything else that you can't really necessarily block for. So here's an example, okay? What would the experiment look like if we decided to block it? So we had 50 men and women. So we still are saying what our experimental units were. We had 20 men and 30 women. Now note, these blocks are not the same. That's okay, but you do want the treatment groups to be about the same size. We're not randomly assigning male and female. We're just splitting them into two groups. Then we're going to randomly assign the men to have caffeine and no caffeine. We're going to randomly assign the women to have caffeine and no caffeine. We're going to compare the pulse rates within this block, compare it within this block, and then we're going to combine all of the results. Now, notice we're not comparing like just this block and just this block. We're not comparing this block to this block. We're combining all of the results to get one big pool of people to see if caffeine affected their pulse rate. All right, so what are some common mistakes? Common mistakes are that people often state they get the vocabulary mixed up between experimental design and sampling. Remember, those are two completely different things. Sampling happens before the experimental design, all right? And then the experimental design is completely different. So don't confuse stratified random sampling with randomized block design. Stratified random sampling is how you're choosing the people to be in the experiment. Block design is how you're carrying out the experiment. The language of sampling experiments are completely different. Sampling happens first, then you create the experiment. Stratified random sampling is done when you take a sample from a population. Okay, so stratified random sampling is we're getting a sample from a population. Blocking is after that's completely done. It's whenever we're assigning units to treatments in our experiment. So we're taking this stratified random sample and using those people in the blocked experiment. So just be careful with that wording because you will lose full credit for mixing up the language of sample surveys, experiment, and observational studies. So for example, if you say, we're going to use stratified random blocking in order to create groups. No, keep them completely separate. Okay, so just take a minute and what is wrong with these following statements? So we used a randomized block design to select the sample for the survey. All right, number one, we don't ever use a block design to select a sample. We use a stratified sample to select a sample. Stratifying is for sampling. Randomized block design is for an experiment. So you could fix it by saying we use a randomized stratified sample to select the sample for the survey. This experiment suffers from non-response since some subjects dropped out during the survey. Ooh, think about that. Experiment and non-response. Experiment is one thing. Non-response is with sampling. Completely different. The experiment's not suffering from anything, but the sample suffers from non-response. So you could say the sample suffers from non-response since the subjects dropped out during the survey. Okay, so why don't you guys take a minute and try this, okay? And then hit pause and go ahead and take a look at the next slide that goes over the answer. Okay, so anytime that you choose a block design, you want to be able to explain why you chose the blocking method that you did. So don't just block without any sort of explanation as to why you're blocking. So why was a completely randomized design not as good? Basically, it ignores the differences between the 4 types of popcorn and will result in a great deal of variability in the number of unpopped kernels for both treatments. Okay, so even though we're going to randomize to both treatments, we're going to have a lot of different variability within those 2 groups. Okay, so for example, if there are many more unpopped kernels in a bag of cheese popcorn and kettle corn than the other 2 varieties, it's going to be harder to tell if there's a difference in the method of popping. So a randomized block design considers each variety of popcorn separately, which allows us to count for the variability in the number of unpopped kernels created by the difference in varieties. All right, so that's explaining why we're choosing a block design. So now, how can we use a block design? I personally like to draw the diagram, but here's a way to do it using a paragraph form. Now notice, we'll randomly assign 5 bags of each variety to each of the 2 treatments. To perform the random assignment, place all 10 bags in a particular variety, large grocery bag, shake the bag, and then randomly select 5 bags to be popped using the popcorn bag. The remaining 5 bags will be popped using the instructions on the bag. Notice how you're explaining the treatments happening to each different group. Repeating this process for the remaining 3 varieties. That's totally fine. If you have a block design and you want to explain the randomization for one of them and then just say repeat with the other varieties or whatever you're talking about, that's totally fine. Just make sure you include that. Repeat the process for the remaining 3 blocks, 3 varieties, whatever. So after popping each of the 40 bags in a random order, we're going to count the number of unpopped kernels in each bag and compare the results within each variety. Okay, so we're comparing the results within each variety. We're not comparing the blocks to each other. We're then taking all of the blocks together and combining the results from all 4 varieties after accounting for the differences in average responses for each variety. So that just means I'm basically taking all of the answers and combining them. All right, so the last type of design we're going to take a look at is called a matched pairs design. A matched pairs design is a type of blocked experiment. When you see the word matched pairs, I want you to remember that matched means similar or the same, and pairs means 2. All right, so with a matched pairs design, what our goal is to create blocks by matching pairs of similar experimental units. Okay, so you're either going to have 2 people, matched pairs that are the same, one person gets one treatment, the other person gets the other, or it's an example of a before and after. Sometimes a pair in a matched pairs design consists of a single unit that receives both treatments. Okay, so a pair could be you doing like a before and an after, or you get both treatments because the pair, you're similar to yourself. Okay, since the order of the treatment can influence the response, chance is used to determine which treatment is applied first for each unit. So what does that mean? Chance is used to determine which treatment is applied. So maybe we are going to have you are going to be a pair for the caffeine experiment, and you're going to drink the caffeine Coke and the caffeine-free Coke. We would flip a coin and randomly assign you one to drink the caffeine-free Coke first or the caffeinated Coke. We're going to flip a coin to decide which one you'll do first. Okay, so that allows chance to say which one will you be assigned to. Okay, so there are only 2 ways to do a matched pair experiment. The first way is to put 2 subjects together that have similar characteristics. For the caffeine example, they could be 2 of the people with the same age. They're both females and the same fitness level. Randomly assign one caffeine and the other caffeine free. Compare the pulse rates between the two subjects. You cannot use more than 2 subjects for matched pairs. Please make sure that you still explain how you're going to randomly assign. In this case, you can use a coin flip. Heads is caffeine and tails is caffeine free.